Question number 11. The acidities of the above compounds increase in the order: A. Metanitrobenzoic acid, B. Phenol, C. Benzoic acid, and D. Paranitrobenzoic acid. Acidity of a molecule is its ability to remove a hydrogen ion from itself. This depends on the level of stability of the anion formed by removing the hydrogen ion from the molecule. The stability of the anion depends on the electron density around the most electronegative portion. Therefore, if the electron density is high, the stability of the anion is high, which makes it easier to remove the hydrogen ion. Comparing phenol and benzoic acid. Phenol forms the phenoxide ion and benzoic acid forms the benzoate ion when they release hydrogen. Given here in orange are the resonance structures of the phenoxide ion. As we can see here, the negative charges are distributed to the oxygen atom as well as the ortho and para positions of the benzene ring. In the benzoate ion, the negative charges are distributed to the oxygen atoms and the positive charge is distributed to the ortho and para positions of the benzene ring. So if we look at the resonance hybrid, the phenoxide ion forms the resonance hybrid with the negative charge distributed throughout the whole molecule, whereas in the benzoate ion, the negative charge is distributed only to the COO group. The positive charge distributed on the benzene ring also pulls electrons from the COOH group, facilitating the release of hydrogen. Therefore, the molecule with the lowest acidity is phenol. Now looking at the benzoic acid to which nitro groups are attached. NO2 group is a deactivator. Therefore, it pulls electrons from the benzene ring. Then electron from COOH group is given to the benzene ring. Therefore, the electron density in the COOH group decreases. Therefore, hydrogen gives its electron and is easily released as H+. Therefore, nitrobenzoic acid is more acidic than benzoic acid. Comparing the structures of metanitrobenzoic acid and paranitrobenzoic acid, we can see the distribution of the positive charges in these two structures. In paranitrobenzoic acid, the positive charge is distributed to the meta position and to the carbon attached to the COO group, whereas in metanitrobenzoic acid, the positive charge is distributed to the ortho and para positions. In paranitrobenzoic acid, as there is a positive charge on the carbon atom directly attached to the COOH group, this pulls the electron from the COOH group more easily than in metanitrobenzoic acid, as a positive charge is not directly on the carbon atom attached to the COO group. Considering orthonitrobenzoic acid, this is similar to paranitrobenzoic acid but less acidic as there is intramolecular attraction present between the nitro group and the COOH group. Therefore, paranitrobenzoic acid is more acidic than metanitrobenzoic acid. So, we have phenol being the least acidic, then benzoic acid, then metanitrobenzoic acid, and paranitrobenzoic acid. Therefore, the answer is 2. 12th question. The IUPAC name of the given compound is. The cation part should be written first and then the anion part with a space in between them. Therefore, this excludes answers 1 and 3. Before naming, we have to deduce the oxidation states of the metals in the compound. In the cation, the amine ligand is uncharged. Therefore, the charge of the metal is solely responsible for the charge of the cation. So, the oxidation number for chromium can be either 2 or 3 according to the answers given. In the anion, each cyano group has a negative -1 charge, giving a total of -6, to which the charge of iron has to be added. According to the given answers, this can be either 2 or 3. So now, if we assume the oxidation state of chromium to be 2, then the total charge of the cation will be 2. As there is only one cation and one anion, the total charge of the anion should be 2 as well. For this to happen, iron should have an oxidation state of +4 to counteract the -6 by the cyano groups. As there are no answers matching this combination, we can safely exclude answer number 5. Now we assume the oxidation state of chromium to be 3. Then the total charge of the cation will be 3. Therefore, the total charge of the anion should be 3 as well. For this to happen, iron should have an oxidation state of +3. This combination is found in answer number 4. Even though we have already arrived at the answer, let's look at how the compound is named. Each ion should be named by naming the ligand first along with its appropriate prefix denoting the number of ligands, and then the metal with its oxidation number in brackets. So this will be hexaamine for the 6 amine groups, chromium 3, space, hexacyano for the 6 cyano groups, ferrate 3, as the suffix ate is added to the metal if the complex is an anion. 13th question. Which of the following arrangement gives the correct increasing order of the bond lengths of the bonds labeled as A, B, C, D, and E in the above molecule? Bond lengths are determined by the type of sigma bond formed. First, we'll look at the hybridization of the carbon atoms as the hybrid orbitals are involved in the formation of the sigma bonds. This carbon is sp3, this is sp3, this is sp, this is sp, this is sp2, and this is sp2. Therefore, bond A will be sp3sp3, bond B will be sp3sp, bond C will be sp-sp, bond D will be sp-sp2, and bond E will be sp2sp2. Generally, single bonds are longer than double or triple bond. The higher the characteristic of the s orbital in a hybrid atom, the shorter the bond. In sp3, the s character is 25%, in sp2 it's 33%, and in sp it is 50%. Therefore, sp will form the shortest bond. So now we can compare the bond lengths. Bond A will be the longest, then we have bond B. Then we have bond E, which is longer than bond D, as bond E is sp2sp2 compared to bond D's sp-sp2. This might seem a bit odd as in the structure given, bond D is a single bond. But in fact, bond D doesn't exist like this. The electrons from the adjacent electron clouds will delocalize to bond D, giving it a partial double bond nature in its resonance hybrid as shown here. In the answer that was given, they have taken that E is shorter than D by disregarding delocalization, which is not the case as you just can't disregard delocalization. Therefore, the answer should be 2. Question number 14. Vessel A contains helium gas at 27 degrees Celsius. Vessel B contains oxygen gas at 127 degrees Celsius. The ratio of the root mean square velocities of the gases in vessel A and vessel B is. Root mean square velocity is equal to root 3 RT over MW. So in this case, for A, we have 3 into R into temperature has to be given in Kelvin, so 27 degrees, so 27 degrees plus 273, which will give 300, divided by helium, which is 4, and for B, we have 3 into R into 400, 127 plus 273, divided by 16 into 2, because oxygen is diatomic. Simplifying this answer gives 2.4. Therefore, the answer is 3. Question number 15. Which of the following arrangement shows the correct increasing order of solubilities of the above compounds in water? Solutes which have molecular attractions similar to that of the solvent generally dissolve well. Compound A has a hydrogen bond. Compound B is a nonpolar alkyl halide. Compound C has 2 hydrogen bonds, and compound D is a polar compound. As the main force of attraction found in water is hydrogen bonds, the compound with the hydrogen bonds will dissolve more easily. In this case, C will have the highest solubility as it has 2 hydrogen bonds, then A with 1 hydrogen bond, then D, which is a polar molecule, and then B, which repels water and is immiscible. Therefore, the answer is 3. Question number 16. Which of the following systems liberates the largest amount of heat upon mixing 1 cubic decimeter of each of the following solutions? The enthalpy of neutralization between a strong acid and a strong base is minus 57.6 kilojoules per mole at 25 degrees Celsius. If either the base or the acid is weak, the energy released will be less than if both solutions were strong. So in 1, we have 0.1 moles of HCl, which is a strong acid, with 0.2 moles of sodium hydroxide, which is a strong base. As HCl is limiting here, the neutralization reaction will only involve 0.1 moles. In 2, here we have 0.1 moles of sulfuric acid, which is a strong acid, which will give 0.2 moles of H+ for neutralization with 0.2 moles of sodium hydroxide. Therefore, the neutralization reaction here will involve 0.2 moles, and it will be roughly twice the heat released in response 1. Response number 3. Here we have acetic acid, which is a weak base and therefore will not liberate all of its H+ from the 0.2 moles. Therefore, heat energy released is less. Response 4 is similar to 3, and response 5 is similar to 1. Therefore, the answer is 2. Question number 17. What are the products obtained when the above compound is reacted with lithium aluminium hydride followed by neutralization of the reaction mixture? The CONH2 group will be reduced to CH2NH2 by the addition of 2 hydrogen atoms. The ester group undergoes hydrolysis in the presence of lithium aluminium hydride, giving the OH group and carboxylic acid. As lithium aluminium hydride is a strong reducing agent, the obtained carboxylic acid is reduced further to alcohol. If sodium borohydride was used, the reaction would stop at the carboxylic acid. Therefore, the answer is 2. Question number 18. The energy required for photoelectrons to be ejected from the surface of barium is 240 kilojoules per mole of electrons. The minimum frequency of light capable of producing a photoelectron in barium is. Here we apply the formula E equals hf. E is energy, which is 240 kilojoules, which is equal to 240,000 joules, which is equal to 6.626 into 10 to the power minus 34 joules second into 6.022 into 10 to the power 23, as they have asked for 1 mole. Simplifying this gives 6 into 10 to the power 14 per second. Therefore, the answer is 4. Question number 19. The maximum wavelength of light that can produce this effect in barium is. Here we apply C equals F lambda. As light travels at 3 into 10 to the power 8 meters per second and F is 6 into 10 to the power 14 per second, we can solve for lambda. Therefore, lambda is 0.5 into 10 to the power minus 6 meters, which is 500 nanometers. Question number 20. The molecular shape and electron pair geometry of G.C.E.A are respectively. Total number of electrons are 8 plus 6 plus 7 into 4, which is equal to 42 electrons, which is 21 pairs. So we have the skeleton of G.C.E.A here. So we draw the 5 bonds which constitute 5 electron pairs, and now we place the lone pairs around the atoms. Here we can form a double bond with Xe and O, and this is the Lewis structure of G.C.E.A. Number of bond pairs around the central xenon atom is 5. Double bond is considered as a single repulsion unit in stereochemistry. Number of lone pairs on central atom is 1. Therefore, the total number of repulsion units is 6. Therefore, electron geometry is octahedral and the molecular shape is square pyramidal. Therefore, the answer is 4.
Hey guys, if you liked our videos, please like, subscribe and turn on notifications. Thank you.